Today we're going to be looking at section 5.8, which is looking at coordinate plane proofs. So unlike traditional proofs that are statements and reasons, we're going to be doing something similar, but we're going to be doing it with shapes that are already in the coordinate plane and using some coordinate plane geometry and algebra to help us solve our proofs. So as you can see in this picture, you have a triangle. And one of the interesting things about the triangle is that even though it looks like we could see the length of the triangle or the height of the triangle, the coordinates themselves are variables. And the reason why we use variables for the coordinates is so that we can generalize our findings. That means that if you have this triangle PQR, all triangles PQR, when finding the midpoint, anything that we can say about this triangle should be true for all triangles since we used variables instead of specific numbers. So looking at this picture, what is the length of the base of this triangle? Well, the way to find the length of it is not to count the little segments. The way to find the length of it is to look at the x-coordinate for r. So because the x-coordinate for r is a, it means that r is a spaces from the origin. Therefore, the length of this triangle is a. We do something similar when we want to find the height. How do we find the height of this triangle? So the height of the triangle is going to be up at point Q. And notice that the height of the triangle should be the y-coordinate of Q, which in this case is C. So these are kinds of things that we do when we do coordinate proofs in the coordinate plane, is we use the variables to help us find the lengths of things. So when you're doing a coordinate plane proof, one of the important things is to correctly place the shape. There isn't really one correct way, but there's definitely ways that make the proof easier and ways that make the proof a little tougher. One of the things that we do is we always place one coordinate at the origin. That's one thing that we can do. Or sometimes we like to put coordinates centered around the origin or symmetric about the y-axis. So you'll see what I mean, but let's take a look at part A. How can I make a rectangle which is 2 units wide and 6 units long? This one's actually fairly easy because we're not using any variables yet. So we want to assign the coordinates in a convenient way. That means it's going to make it as easy as possible. To me, I think working in the first quadrant is the most convenient. All the values are positive, and picking the origin is one of my vertices. So there's my rectangle. Notice that I made it 6 units long and 2 units wide. So now I want to assign all the variables to it. All right, let's try part B. This time I want to make an isosceles right triangle with 4 unit legs. Some of you may be tempted to make it look something like this. But you're going to have a really hard time guaranteeing that this is a length of 4 in the leg, since you're making the leg diagonal. So a better thing to do in a problem like this is actually to make the legs vertical and horizontal lines. It's a lot easier to measure that the legs are going to be a length of 4 if they're horizontal and vertical, rather than if you had made the legs on the diagonal. Since we don't really care what the diagonal is, we'll find the legs first. That'll make it easy to find the coordinates, and then we'll label all the coordinates for A, B, and C. And then we'll have our isosceles right triangle. Okay, so when we talk about placing it in a convenient way, it means that it's easy to find the coordinates. It means that it would be easy to find the lengths of things, like the lengths of this isosceles triangle. And generally, when we get ready to set up the proof, we do lots of work with finding lengths of things or finding slope. So it's nice if we place things in a convenient way. So let's take a look at these examples. These ones say to graph the triangle with the given vertices and find the length and slope of each side. So you might notice that these ones have variables, and you might be wondering to yourself how you're going to find the length and slope of something with a variable. The answer is you're still going to use the slope formula or look at the length. You're just going to have an expression that involves a variable instead of a number. So let's take a look at the first one. So I'm going to plot A, B, and C. A is easy to plot, that's 0, 0. B and C are harder to plot because we don't know what A is. So in this case, the drawing is just there to sort of help me and support me. So what I'm going to do is I'm going to choose an a that's sort of a convenient value. In this case, because they're asking me to find the midpoint of things, I'm going to choose a value of a which is an even number. So just out of convenience, I'm going to choose that a is 4. So I don't write 4. Notice that I still call it a. So b is a coordinates from the origin and 2 spaces up. And then I can plot c. C is a spaces from the origin and 0 spaces up. So here's my triangle. And now I have quite a bit of work to do. I need to find the coordinates of the midpoint of each side. Okay, so notice that this triangle has length a and height 2. Okay, so that's important. And we can also find the midpoints. So this midpoint has the same coordinates as B and C. It's on the same vertical line. So what I would notice about this guy is because he's on the same vertical line with points B and C, it should have the same x value, which in this case would be A. But it's half the distance up to B, so the y coordinate is 1. So I'm going to do the same thing as I find the midpoint of the other side. So there's the midpoint, right? And this midpoint, I notice if the entire length of this is a, then it should be halfway across the entire length, and that makes its x-coordinate a over 2, but it's sitting on the x-axis, so then it's going to have a y-coordinate value of 0. So if we're finding the slope of these lines, right, if we're finding the slopes of the sides, we would do the same thing. If I wanted to find the slope of BC, I would do y minus y over x minus x, and I'm going to get an undefined slope because the denominator is 0, right? And similarly, if I'm finding the slope of the other leg, which is AC, I'm going to take the y value minus the y value over the x value minus the x value, and I'm going to get 0 over negative a, and I'm going to get a slope of 0. So since one line is a vertical line and one line is a horizontal line, we do know that this is a right triangle. And then it asks, is this triangle isosceles? And this triangle is not isosceles in our picture, but remember that because we don't know the value of a, we need to specify that this could be an isosceles triangle if a had a value of 2. All right, let's look at the second problem. So first thing I'm going to do is plot my points. Again, I don't know what a is, and I don't know what b is, but because I'm going to be finding the midpoints, I chose a and b to be convenient, so even numbers. I also chose them to be different from each other. If in the problem they were meant to be the same value, they would have used the same variable. So again, I want to use different values. So there's my triangle. Notice that the height of this triangle has to be a, because that is the y coordinate for k, so it's a spaces up. And the length of this triangle has to be b, because that is the x coordinate of point L. So again, I can use the picture to kind of help me find the midpoint. Notice that the midpoint is halfway up, but still has an x value of 0. So we expect the x coordinate to be 0, but the y coordinate to be half of a. We can do something very similar for the midpoint at the base of the triangle. The x coordinate we expect to be half of the x coordinate to L, since it's halfway to L, so that would be b over 2, but it's on the x-axis, so we expect the y coordinate to be 0. Oop, let's fix that. Okay, so now we can find the slope of each of the lines, and we would find it the same way we found in the last problem. Obviously, we're going to find that the slope of JK is undefined because it's a vertical line, and we're going to find the slope of JL to be 0 because it's a horizontal line. So we can definitely decide that this is a right triangle, and we can also decide that this triangle is not isosceles. Again, if A and B were meant to be the same length, they would have used the same variable. So given that they use different variables, we know that those are different lengths, and therefore it's not isosceles. All right, let's take a look at this next example here. Find the coordinates of any unlabeled vertices and then find the indicated lengths. So first let's take a look at this. There's some vertices that aren't labeled. Obviously this is going to be 0, 0, right? And then it looks like B is H spaces over from the origin, so that makes C the point H, 0. So what else do we know about this problem? Okay. We know that the length is going to be H. And we know that the height is K. And that's really all that we needed to do here. All right, so let's look at part B. Oh, we needed to find the length of OB. Okay, so OB is the hypotenuse of a right triangle. So we can use the Pythagorean theorem. So OB is going to be A squared plus B squared, or H squared plus K squared, the sides of the lengths. And since H and K are different variables, we're not going to be able to simplify. And that means that this is going to be our final answer, the square root of H squared plus K squared. When we work in coordinate proofs, we always expect to get expressions which can't be simplified because they involve lots of different variables. Okay, let's take a look at part B. So one of the things that I need to do is I need to find the coordinates of point D if I'm going to find the length of FD. So I notice that F is negative 4K spaces down from the x-axis. But since these two triangles are congruent to one another, if F is negative 2 and negative 4K spaces down, then D should be positive 4K spaces up. And similarly, if F is negative 2 spaces back from the origin, D should be 2 spaces forward from the origin. So that's one of the ways that I sort of think through how to find the coordinates of D. Right? D is sort of a mirror image to F, and therefore D has coordinates 2, 4K. So now we can find the length of FD. Since FD is made up of two congruent segments, F to O and O to D, we know that FD is going to be twice the length of DO. So we can very easily find the length of DO. DO, we'll use the Pythagorean theorem, 2 squared plus 4K squared, and then we'll square the terms on the right-hand side and then take the square root. Right, so DO is going to be the square root of 4 plus 16K squared. And then all we have to do is double DO to find FD. So FD is going to be 2 times the square root of 4 plus 16K squared. So now we need to find DE. Okay, so here's triangle DE, this turquoise triangle. DE, again, if we apply the Pythagorean theorem, right, it's going to be this distance here, right? That's one of my sides of my triangle. How you find that length is you subtract the x value from this point and the x value from this point, right? That's how you find the length between 2 points. You subtract. So that distance is 2h minus 2, that's one side, squared. And then the other length of my triangle is this one, which is 4K. So that's where I got the 4K squared from. So now to solve for DE, we'll multiply everything out on the right-hand side and then take the square root. And that's DE. So you'll notice lots of different variables. We're not going to be able to simplify. None of these terms are like terms. You've got squared terms, linear terms, constants, and two different variables. So we'll leave it just like that. All right, let's take a look at another type of coordinate proof which we can do, and that is putting all these pieces together now to prove similar things that we've proved in the past, but just in a different way. So take a look at this problem. You've got the coordinates of vertices of this quadrilateral, and we're trying to prove that these two triangles are congruent to one another. Now, in the coordinate plane, it's actually very tough to know the actual values of the angles until we have some trigonometry. So we're going to be proving these triangles congruent by SSS, side, side, side. So if I'm going to prove this by side, 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 first thing I'm going to want to do is I'm going to want to show that OT is congruent to UV. So I'm going to find the lengths of these two sides, and I'm going to find them the same way that I would find them in the previous problem. I'm going to apply the Pythagorean theorem, right? So here's the triangle that I have. The height of this triangle is clearly K. The length of this triangle is M. So that's how I'm using this to find the lengths. Okay, so now we're going to, we found that side. Now we want to show that TU is congruent to VO. So to find the length from T to U, again, this is like in the last problem, to find the length of a segment, you take the X coordinate of this segment further to the right and subtract the X coordinate that is on the left. So the length of TU is going to be M plus H minus M, which is H. And then we can do the same thing down here to find the length of VO. We're going to do H, the X coordinate here, X2, minus the X coordinate here, X1. So we find that VO and TU both have a length of H. So check, we've just found that those are the same length. So lastly, we can look at OU. We know that OU is congruent to itself by the reflexive property, and that creates our third side. So now that we've done all this work, right, coordinate plane work, finding lengths of things, we can say thus triangle OTU is congruent to triangle UVD by side, side, side. Let's take a look at one more example. So we want to do a similar thing in this problem. We're trying to prove that two triangles are congruent. We're going to be using SSS, and one at a time we're going to find the lengths of these sides and then conclude that if all three lengths are congruent, we've proved congruency. So first let's show that AC is congruent to BD. This one's actually a lot easier, right, because these are vertical lines. So again, to find the length of a vertical line, we're just taking the y coordinate and subtracting the y coordinate. So AC is going to be equal to K. And by a similar method, BD is also equal to K. And we can check that off our list. That's one side we've shown congruent. So now we want to show that CO is congruent or equal to DO. And again, to find the length of horizontals, you're doing the right-hand most x-coordinate minus the left-hand most x-coordinate, so U minus a minus H. And that makes CO equal to H. And we do a similar thing to find the length of DO. DO is equal to H. Check, we've just shown that another set of sides is congruent. So then the last thing we need to do is show AO and BO to be congruent. These guys are going to be a little trickier because they're diagonal. We're just going to apply the Pythagorean theorem. So AO squared should be negative H squared plus K squared, making AO the square root of H squared plus K squared. So by the exact same method, we find that BO squared is H squared plus K squared, and BO is the square root of H plus K quantity squared. Sorry, square root of H squared plus K squared. So there we have it. We've shown all three sides to be the same. And now we conclude that triangle ACO is congruent to BDO by side, side, side. When you do coordinate proofs in paragraph form, you don't necessarily have to say statement, reason, statement, reason. For these types of proofs, it's sufficient to write what you're trying to show and then do the algebra underneath and then write one concluding paragraph.